This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, let's start. Good afternoon, guys. Let me first do some debts that I've accumulated, even not all. Please remind me if I forget the laser pointer on the slides, all right? We'll get here later, I hope. Okay, so in the meantime, I'll have both of them like that. Okay, so last lectures, I very quickly went through this set of slides, and today I want to finish what's important for you guys to know. So the discussion here goes about joints, constraints, and degrees of freedom, because these things are all related. Okay, so for degrees of freedom, what we will need to do for a mechanism, we will need to determine how many degrees of freedom are there for a given system. Okay, how many degrees of freedom we will need to find out. And for the same number of degrees of freedom, we'll need to produce the same number of equations of motion. All right, so if you're asked, find the equations of motion for some system, first think how many degrees of freedom does this system have, and then you know at least how many equations of motion you're after. All right? And in order to determine how many degrees of freedom are there, we are going to look at the joints that connect different rigid bodies in the system. And for each joint, depending on the structure of that joint, there will be some constraints associated with that joint. And as a result, a reduction of the possible degrees of freedom. Okay? Now, the possible degrees of freedom for one rigid body that is not constrained in 3 dimensions, I mentioned it is 6. Okay, so for one rigid body, 6 degrees of freedom if there are no constraints. Okay, now if you have several such rigid bodies without taking into account any constraints, you just multiply 6 times the rigid bodies. That will give you the number of kind of initial degrees of freedom you're starting with before you take away any degrees of freedom due to constraints. Okay, now in 2D, we start with 3 degrees of freedom per rigid body. Now, do the numbers 6 for 3D and 3 for 2D make sense? Yeah? So 6 would be 3 rotations and 3 translations, and 3 would be, in 2D, would be 2 translations and 1 rotation. Okay, so remember that. A little story. There was a student who was going through an oral exam because they failed some previous exam after exam. So they had an oral exam with me and my supervisor, let's say, and they were asked, for one rigid body in 3D, how many degrees of freedom are there? And that person didn't answer correctly. Okay, they didn't say 6. And after less than 5 minutes of the start of this oral exam, my supervisor said, okay, you failed. Okay, so this is something so basic I want you to understand, okay, because I felt ashamed as if I didn't teach it right. Okay, so is it clear? Is it clear without any constraints? Okay, now with constraints, we will look at every joint. And I already went together with you last time. We saw for this joint, there are so-and-so degrees of freedom, some rotational, some translational, and we classified some examples, all right? So all of this comics thing, do you want me to go through it, or do you want me to skip it? Shout louder. Skip it. Okay, I'll skip it. Thanks. So just let me know if you want me to go through it in consultation or something like that. Now here I have an example of universal joint. Now let me apologize. I gave you one handout when we were talking about parallel access theorem, and there was this swing, and for the swing there was a 2 degree of freedom joint at point O, and I wrote universal joint, but it's not. So it's a different type of 2 degrees of freedom rotational joint. So this one is a universal joint. Okay, so the 2 axes of rotation are well, you can try to look here and figure out. I'll just explain a bit better. So there is one rigid body here, which is connected to this, let's say, this rigid body, yeah, and the other side here, let's say, is connected here, okay, to the other rigid body. So this end and this end, they are the 2 connected rigid bodies, yeah, and whatever happens in between them is like a zoom in into the joint between. Okay, so this is, if I say here, it's written, sorry, it's a bit too low, but it's written universal joint. Okay, so this is how it looks when you zoom in. Okay, so you can see this cross can rotate about this axis. Okay, actually it is rotating about the negative y0 axis here. So I have the black frame 0, connected to this part. Okay, it doesn't mean that it's stationary, but I have frame 1 as an auxiliary frame that defines the orientation of the cross here in between relative to this body. Okay, so frame 1 is attached to this cross, and frame 2 rotates around this cross, around negative axis x1. Okay? So that's another degree of freedom. So 2 degrees of freedom in this manner. And this assignment of frames is just an example. Okay? You can follow a different assignment of frames. You can just decide for yourselves according to the convenience. Okay, but you will need 2 degrees of freedom. Okay, so maybe I think I called it maybe, yeah, alpha and beta. So alpha and beta. So alpha would be the rotation of the cross along the negative y0 axis, and beta would be the rotation of this upper link here relative to the cross about the negative x1 axis. Okay, so these are the 2 degrees of freedom and the 2 parameters that I could assign, alpha and beta, for representing what happens here. Okay. Now, do you understand for universal joint what happens inside? Yeah. So this is just one type of joint, 2 degrees of freedom. Okay. So for a system like this that has one universal joint and one fixed rigid body or stationary body, okay, and this one, all of this rock plus rod, all of this together is one rigid body. There is no relative motion between the rod and the rock. So for all of this system like this, there will be 2 degrees of freedom. Okay? Now you can think of it in a kind of summation way, starting from 0 and adding 2 degrees of freedom because of the allowed motion here, so 2 degrees of freedom, or starting with one rigid body that can move, so 6, and then reducing 4 for the 4 constraints due to this joint. So the 4 constraints are 3 linear motion, so x, y, z, all directions are not allowing motion, okay, and 1 rotational constraint because there is no, say, no allowed rotation about this Z2 yet. So overall, this joint does not allow 4 types of motion. Yeah. So you can either go 6 minus 4 or 0 plus 2. Now, because here this mechanism is serial, meaning it's like a chain of rigid bodies. There is no coming back to the start, no closed path of material, let's say. You can do this plus summation, so 0 plus 2. Okay, but if you had if you had this rigid body constrained in another way to say this rod, you can't do this. You need to only take away the constraints. Okay, so I will go forward. I think I talked about this example, right? So for this one, I mentioned in the additional way, this is a serial mechanism as well. Okay, so it's like a series of joints with only one direction, and then you don't go back to the start. So you don't constrain the last, or you don't constrain any of the links in that serial mechanism back to something else. Okay, just one end is constrained. So I did 3 degrees of freedom here and 1 degree of freedom here, so in total 4. All right? Or I can do the takeaway method. So 2 rigid bodies. I start with 12 degrees of freedom because it's a 3D space. Okay, so 6 plus 6. So from the 12, I will need to take away any constraints of motion. So I will take here, for this joint, I will take away 5 because I don't allow 2 rotations and 3 translations, and I will take away here 3 for the XYZ, 3 translations that are not allowed. Okay, so 8 overall, 5 and 3 constraints. Okay, 8 constraints. These constraints, remember these 8 constraints, I can represent each of them as an equation using parameter. If I specify 12 parameters in a way that can represent all the points along this system. Okay, so if I assign 12 parameters, I can use these parameters, and the next slide gives you one example of how I can come up with 8 equations. So these are 5 equations, and these are 3 equations. So 8 equations overall to specify each constraint in a mathematical equation form. Okay, so these 8 constraints, starting from 12, 12 minus 8 is 4. And in addition, these 8 constraints also represent 8 components of either force, if the motion that is restricted is linear motion, or moment or torque, if the motion that is restricted is angular motion. Okay, so we will take it into account when we do free body diagrams. And we went through these examples, and I wanted to just finish with this example. And I changed the slide, the writing, because it wasn't clear. So if you look at this mechanism, I didn't talk about it, right? I didn't go through it. Okay. So what is here? This is a blue disc that can only rotate around this pole, vertical pole. The vertical pole is fixed. Okay, it doesn't move. Okay, so it only has, well, this joint only has 1 degree of freedom revolute. Okay, so rotational. This green disc can move up and down and rotate. So both of these things. So it has how many degrees of freedom? 2, but it's more related to the joint here. This joint is a cylindrical joint, meaning we can rotate and go up and down. Okay? And there is this rod here connected at point A using a universal joint. This is the one with the 2 degrees of freedom, as I showed you before. Yeah. And with a bow joint or spherical joint at point B here, which is like a ball and socket. All degrees of rotations are possible and no translation. Okay, so how many degrees of freedom here associated with B? 3, all kind of rotational. Okay, and with A, 2 degrees of freedom rotational. Okay, so the question is to find the number of degrees of freedom for this system. Okay, so you can imagine how the 2 discs can rotate, and this rod, the black rod, will be adjusting itself. So what you can do is say, okay, there is 1 rigid body, 2nd and 3rd rigid body, because this vertical rod is stationary, we don't need to count it. So we can go 1, 2, 3 times 6, 18, and from 18 we need to decrease all the constraints in the system. Okay, now this system is no longer serial, because it's not like the green disk is the last link and it is not connected back. It is because there is like this closed path here. Closed path, so it's not a serial link. I can't just go 1 degree of freedom plus 2 degrees of freedom plus. Yeah, I can't do this plus this plus this plus this. It won't represent correctly this system. Okay, it will represent the system without point C connected back to here. Okay, so this is the computation here. So 18 minus 5 for joint O, minus 4 constraints for joint A, minus, say, another 4 for joint C, okay, and minus 3 for joint B. Okay, so you end up with 2 degrees of freedom. So if you want to model this system, you will need to find 2 equations of motion. Okay, you will need to find 2 equations of motion because there are 2 degrees of freedom. Okay, now what you can do is find the 2 equations of motion using, you will need to use eventually 2 parameters. So let's say alpha and beta. Okay, now you can choose these parameters in infinitely many ways. Okay, one example is, say, some theta 1 that is rotation of the blue disk and theta 2 that is rotation of the green disk. And with these theta 1 and theta 2, you can represent the motion of the entire system. So the constraint equations can relate between theta 1 and theta 2 and all the other parameters you may define as just auxiliary parameters to find the orientation of the rod or things like that. Okay. Yeah, so when you come to analyze this system, what you will do, you will start by writing the Newton-Euler equations for each rigid body. So you will need to write the free body diagram for each rigid body. So you will probably draw the blue disk separately, the black rod separately, and the green disk separately, each of them. You will put all the forces and moments acting on each, and for each you will write the Newton-Euler equations. For each there would be 6 scalar Newton-Euler equations, right? 3 linear, sigma f equals p dot, and 3 angular, sigma m equals h dot, right? So 6 equations for each, and out of these equations you will need to let's say organize them and get rid of many equations and just be left with 2 equations that will be your equations of motion. I will explain later today. And these equations of motion, what will be special about them is that there will be no unknown constraint forces or constraint moments, no components like that in these equations. Okay, so all they will contain is, for instance, if you are using theta 1 and theta 2 as your parameters, all the equations of motion will contain is theta 1, theta 2, and their derivatives, and any actuation forces or torques, depending on the definition of the problem. Okay, but nothing unknown other than theta 1 and theta 2 inside the equations of motion. Okay, so just to sum up, how many Newton-Euler equations will you write for this system? How many scalar Newton-Euler equations? So for each rigid body, you will write 3 linear, scalar equations and 3 angular scalar equations, yeah? So overall for this system, how many scalar Newton-Euler equations will you have? 18, yeah. And how many equations of motion will you need to find? 2, okay? 2 as the number of degrees of freedom. Okay, now this is the last example I want to explain. For this set of slides. So what do you see here? There is this L-shaped bar or link, yeah? And imagine here there is like a stationary floor, and this entire thin L-shaped link is rotating with a constant angular rate of change here, omega. So omega is constant. It is given in the problem that this thing rotates in a particular manner. Okay, now what is important for me to say, even though it moves, the motion here is prescribed. Okay, it is prescribed, it is given as if there is someone here, maybe servomotor or a person, something, makes sure that it rotates with this omega, never mind what. Okay, so this rotation with omega is not a degree of freedom. It's not a degree of freedom because there is no freedom despite it being in motion. Okay, so motion is not necessarily degree of freedom. If there was no, if it wasn't specified that it rotates with constant omega, or it doesn't have to be constant, anything, any specified motion, someone making sure it moves in a particular manner, if it wasn't specified like that, then there would be one more degree of freedom for allowing rotation. Okay? Is it clear? Not so clear? Maybe if you think of these as two links, okay, two links, just this mechanism, yeah? If this is two links, then if I look at, if this is only revolute joint and this is only revolute joint, yeah? Now, normally it would have 2 degrees of freedom. But if I specify the motion for one of them, let's say I say this has to go like that, never mind what. So this angle is doing some prescribed motion, okay? A known one. So if the shoulder one is not prescribed and it moves kind of as a result of everything else that is happening, then I will only have 1 degree of freedom here, okay, for the shoulder. Okay, does it make sense? Yeah? Okay. So this is one rigid body here. It is connected to 2 sliders with these points able to rotate. Okay, so you can think, and this is, because of this connection, this is not a serial mechanism. It is parallel, okay, because there is this closed path here. And you can think how many degrees of freedom this mechanism has by decreasing from what you will do here. Let's say if this is massless and this thing just does this rotation, you can even ignore that, because you know exactly how to represent the position of every point here over time. You know how to explicitly present the configuration of this L-shaped bar. So it's just a matter of looking at the clock, what is the time, and according to the time you know where this L-shaped bar is. Okay, so let's say if at time 0 it's here, after 1 second it's omega radians there. Okay, this L-shaped bar. So essentially you just have kind of this rigid body in a plane that rotates in a predicted way. Okay, so this rigid body in a plane that rotates in a predicted way. And you need to think, there are several things that you can do. If you want to think in 3D, you can look at this one rigid body initially having 6 degrees of freedom and then looking for all the constraints. Okay, so you will need to maybe select 6 parameters to represent, say, the position of some point of interest on this rigid body and to represent its orientation. So you will need 6 parameters to represent the position of some point and the orientation of this rod. Okay, and then with these 6 parameters, you will need to come up with all the constraint equations to say, okay, this cannot move there, this cannot move there, okay, the algebraic constraint equations. One of them will necessarily include this omega. One of them will be like some angle equals omega t. Okay, let's say if you define this angle as alpha, one of your parameters, so alpha equals omega t, is a constraint equation, all right? It's just that it depends on time. Okay, if a constraint is time dependent, it is called rheonomic, so you will see it in the last slide. Okay, so this is if you treat it in, say, 3D. If you already figured out that it doesn't matter how it rotates with this omega, it doesn't contribute any freedom, then you can treat this as a link in 2D, okay, and come up with 3 parameters, okay, and then find all the relevant constraints within this plane, okay, just within this plane as if it's a planar problem, okay? Or, even simpler, here in this example, what you can do is think about the minimal number of parameters needed to fully represent the configuration of this system. Okay, so how many parameters are needed to know exactly where every point on this system is? And the answer is 1. 1 parameter, either this angle, or say this height. Choose some single parameter correctly. I mean, not like every parameter is fine, but many parameters could be chosen for this task of representing the configuration of the entire system. You can choose, say, the distance from here to this point. Okay, it won't be a very good choice, because if it goes to the other way, this distance won't be like very specific of whether it's here or here. But if you choose, say, coordinate along this axis, or as in this slide, this angle, a single parameter can determine the configuration of the entire system. Okay, again, given that this rotates with a known motion. Okay, any known motion, not necessarily constant. but something prescribed. Okay, is it clear? All right, so if you have any questions about degrees of freedom, determining the number of degrees of freedom for a given system, if you're puzzled, because you will need to look at different examples and figure out for each example, okay? If you find yourself too puzzled, let me know in consultations. Now, in advanced dynamics, we go much deeper into this topic. In this subject, all I want you to know is kind of quickly finding out how many degrees of freedom there are for not very complicated systems. And then, based on this number, knowing how many equations of motion you need to come up with. Okay, so I will say again this example with the gyroscope that you saw in the lab. What happens in that gyroscope? Assuming that the bottom, point O, is a fixed point, and it can rotate in all directions, this bottom point, point O, behaves like what type of joint? Like a ball joint, right. So it allows 3 degrees of rotation and no translation, right? And in addition, you have the rotor rotating about 1 axis. What type of joint can you model between the rotor and the frame of the gyroscope? It's a simple revolute joint, okay, revolute joint. Now, so it has 1 degree of rotation, okay? And this system is a serial system if you think of the 2 points where the rotor connects to the frame as just 2 points which are essentially the same joint, as if the center of that joint is at point G, the center of the rotor. Okay? I will talk about that soon. Okay, so I'm done with this lecture. And I wanted to complete this one. So I changed for this one as well some slides. Okay, so this is for drawing free body diagrams, and I went roughly I went through this example. Yeah. So this example was how to draw free body diagram for well, using components. Okay. Here using components. So kind of 2D or projections onto planes. All right. And then it allowed us to sum the moments and the forces. Yeah. So that would be useful for constructing Newton-Euler equations. All right, the sigma f and the sigma m part. Any questions about that? Is it clear? Did you have time to look at it? No time to look at it? But didn't you have practice on that during the tutorial? Okay. So for this example, I was drawing a slightly different free body diagram with here these vectors. I keep them as vectors, okay? So this minus here and this minus here, without the minus here, they represent action and reaction. Okay, they represent action and reaction of one another. You just need to have a minus at one of these places. Yeah? It's out. Okay, sorry. Thank you. Yeah, thanks. Keep reminding me, sorry. So this minus and this minus here, they represent, so they stand for reactions to here, F and M. All right? You could put the minuses here and no minuses here, okay, as long as you put the minus sign in one of them. Okay, so it's just to say if this link applies FO on this link, then this link applies negative FO on this link, okay, where FO is a vector, okay, a vector, and then I need to choose some coordinate system and specify the 3 components of FO along the axis of that coordinate system, okay, and I need to do that for each of these vectors of forces or moments here. So I did it here for all the forces and moments appearing on this diagram. Okay, so this is the vertical link. Okay, and I randomly chose to do it all in frame 1 that is attached here to this link, but I could do that in other frames. Okay, however, frame 1 gives a good choice of representing this MA and MO with one component here. So let's say for MA, because the joint in A allows rotation about Z1, let's say. Yeah, so if it is actuated, then there would be a torque in this Z1 direction. And I can call this torque tau 1. This torque is something known in your system, okay? How much torque the motor supplies, okay, over time. If there is no actuation here, then instead of this tau 1, I would put 0. 0 as nothing, no moment reaction or no constraint moment is applied in the Z direction here, because this rotation is allowed. Okay, so if there is an actuator, put some actuation torque or driving torque here. This is tau 1. If there is nothing, put 0. Okay, in the relevant component. Here at point O, there is allowed motion about x1. I will show you. Yeah, so look at joint O. Yeah, this wing can move about x1 or negative x1, doesn't matter. So yeah, so you see how it rotates around x1, and therefore if there is a motor or an actuator there, then the component here of the x component of the moment between this link and the second link, the moment component has to have this driving torque at the x component. If there was no actuation, you would put here 0. Okay, would you like to ask me if anything is unclear? Or do you understand why there is tau 2? Yeah, clear? Okay. So let me jump through this. Did you understand how to do these summations of vectors to get the resultant force, the resultant moment for each link? Is that clear? No? Okay, someone asked me, why am I doing R cross F? Why R cross F? Yeah. So apparently some of you are happy with R cross F as a 3D moment, yeah, calculation due to some force. And if you are only used to two-dimensional kind of just multiplying distance and force in some direction, so this cross product will give you all the directions of the moment at the same time. Okay, so you will need to try and convince yourselves, I guess. Okay, so are you happy with how this is done? Let's say for this example, I'm doing sum of moments about point G2. So in order to take into account this minus FO force at O, I need to go from G2 to O, so this is this vector here, and cross it with the force, minus FO. All right? Okay, this is maybe trivial, I don't know, someone asked me. Okay, last example. What happens here, I need to separate two free body diagrams. So I'm taking this kind of Z-shaped axle and the wheel, all right? And what happens at each point? So here, this point here, I called this point A, and this point B. Now, together, well, okay, sorry. This one doesn't allow what type of motion? It doesn't allow translation in any direction. Imagine it's like holding in all directions, okay? Whereas this one allows passing through. So this one is like a cylindrical joint here, allows rotation and passing through it. Okay, and here at this point O, it is what type of joint? Revolute joint. Okay. Yeah, so this one here is, I think, passive, totally passive. I think here there is, if I'm not wrong, driving torque to rotate. Okay, driving torque, and possibly a driving torque here between this wheel and the shaft. So this is just the shaft in a kind of initial or naive, I would say, free body diagram. Okay, so here are the forces and moments at A. They need to account for, so this one, no translation. Okay, so it will have all of the components with some kind of FAX, FAY, FAZ, right? And this MA, it will have either a driving torque if there is an actuation, or 0 in the Y1 component, okay? Because there is allowed motion around Y1, okay? And okay, I will just skip it. So this is what I had before on the slides. Okay, so you can see here, say, tau 1 in the Y1 direction. Okay, if there was no actuation, this would be 0. Okay, now I wrote here too many unknowns. Why? Because if you count the number of unknowns, you have 3, that's 6, 7, 8, 9, 10, 11, 12, 13, 14. And you only have, so you have 2 rigid bodies here, the shaft and the wheel. Okay, so you have, like overall, you start from 12, and then essentially you have let's say 2 degrees of freedom, or maybe even just, 2 degrees of freedom. So from 12 minus 2, you need to remain with 10 constraints, 10 constraint components. Okay, and so what happens here, it's too much. You won't be able to find them. And this is because the force at B and the force at A, yeah, if you imagine this shaft resting at A and B, it doesn't matter to us, or we won't be able to distinguish how much of the force reaction from the ground, let's say, falls at A and how much at B. You won't be able to determine what happens at A and what happens at B in terms of force. It's like together. It's like in your gyroscope, the two connecting points, top and bottom, you are not able to say what of the constraint force components is at the bottom and what is at the top. You treat both of them as a single joint centered at G. Okay, so point O and point C, yeah, or let's say more sorry, I forgot to bring with me some paper. So this point and this point on the gyroscope, if you remember, you kind of treat them as a single joint here, right? Centered here. So you don't mind which part of the force is here, which part is here. It's like a single joint, like a long revolute joint. Okay, centered here. Does it make sense? Okay, so when you are doing free body diagrams, you will make, so let's say for the rotor, at this point G, you will look at the force, yeah? Okay. And the moment and other things, I'm not drawing all of the entire free body diagram, but so this is fine, but if you will do this and this, some kind of, let's say, F1 and F2, it will make too many unknown components for you. So this example will make just 3 components, okay, and this one will make all 6. Okay, so this is not good. Okay, hopefully. Gradually, I'm trying to make a point. Okay, so what happens here at B, if you want to resolve it, this FB x1 and this FA x1 and this FB z1 and FA z1, they are essentially, you can treat them the same for the sake of dynamics modeling. Okay, so I changed it to this kind of way. FA only takes care of the no horizontal motion, okay, at A, and it has only one force component, and I put here FAB as the center of these 2 joints, preventing motion along X1 and Z1. Okay? Have a look. So FAB is the force that the ground applies on the shaft. FO is the force that the wheel applies on the shaft. Okay, so on the wheel you will have this minus FO, minus MO, but nothing with this FAB. All right? Any questions? This is a replacement for having the two FA and FB in this fashion here. So here you have 1, 2, 3, 4, 5 unknowns. Here you have 1, 2, 3 unknowns. So this should be fine in terms of overall number of unknowns and the number of equations you will be able to set up. Okay? So I'll have a break now. Okay, so I'll come back in about 10 minutes. Let's continue. Thanks for waiting. very important for me to disappear for some time. Okay, so just to sum up this example, if we combine FA and FB to something like that, or let's say just 3 force constraint components, 3 in total, yeah, 1, 2, 3. So instead of these 5, we will only have 3, so 3. And I keep counting 4, 5, 6, 7, 8. This is not an unknown, this is known. So 8, 9, 10, 11, 12. Yeah? So let me see. Okay. Tell me before. Okay. So for this link, yeah, I'm trying to count. Guys, I'm a bit confused about that. I will summarize it and email it to you because I don't want to post for too long. Okay, so I'll keep going to the next lecture. Sorry. Okay. So this is the next topic. And for this one, I wanted you to grab this, all right? So I'm going to define many things, and this will help you kind of look and see what's going on, all right? Everyone has one? Yeah? No? You have? You can take a copy from there. Okay. So what we are going to do is, it's important for me to say in advance, what we are going to do is like a framework. What I'm going to do is to generalize the approach of writing the 6 scalar equations, the Newton-Euler equations, for each link in a mechanism, a serial mechanism. And this is to show you the feasibility of getting equations of motion at the end. So this is like a general example, okay? It's general enough, but when you come to actually apply it, unless you have a system with many links connected, unless you have such a system and you want to automate the computation of the equations of motion, I suggest that you work kind of case by case. You don't follow blindly this approach that I'm showing today. Okay, don't follow it blindly. It's just a kind of demonstration of concept in general. All right, but it is still helpful to understand it completely, and all the formulas you will see. I don't expect you to remember any of the lengthy formulas, just to understand them, understand how they were constructed and how you would construct such equations from scratch, given some specific example. Okay. So I will show this method on a specific example, and then later on you will see different systems and you will be applying this approach with the necessary modifications to every system. Okay, so Newton-Euler, yeah. What we are doing essentially is writing the 6 equations per link. Okay, the 3 linear, the 3 angular, per link for each link. But these equations, you can write them in general. Each let's say each vector equation, the sum of forces equation or the sum of moments equation, you can write in a system, in a frame that you want, okay, any frame. But if you will mess up the frames too much, it will be hard for you to eliminate the unknowns and only end up with the equations of motion. So I'm showing you a strategy that will always yield the ability to quickly extract the equations of motion, okay? Instead of you having a mess of equations and struggling to untangle them to extract the equations of motion. And this strategy or this approach is called, say, Newton-Euler approach, okay, for writing the equations. And it consists of two parts. So the two parts is doing the kinematics calculation. So that's the, let's say, if you have, sorry, I will, as I said, I forgot to bring blank pages. So you have, let's say, sigma f equals p dot and sigma m equals h dot. So the forward thing is to get these ones. Everything you need for this part. This is the forward kinematics. And what I mean by forward is going from link 1 to link 2 to link n until the end, this direction, from link 1 onwards to link n. And this part, they are all vectors, yeah? This will be the backward or the reverse dynamics. Okay, so the backward means going from n back to 1, link after link, analyzing link after link. Okay, so this is an iterative approach of two parts. Okay, first we go from link 1 to link n to obtain everything here, and then we go from link n to link 1 to obtain everything here. All right. Now, at the beginning, I'll just specify our assumptions and all of the kinematic stuff that we will need, all of the forces, moments, all the definitions, okay? All right. Okay, so this is just like a quick review. For each rigid body, we can write these 2 vector equations or 6 scalar equations, all right? We can write them in any frame that we want, right? And I promise to explain how to do it in a systematic manner. So what we will discuss is how to apply how to write these equations a bit more specifically for systems that look like this, that are essentially serial systems. And the black joints here, they represent joints that are not necessarily revolute, like in the picture. It could be any type of joint, but every joint is just 1 degree of freedom joint. So we will imagine a serial chain or a composition of links connected between them, such that between each 2 links, 2 neighboring links, there is one degree of freedom joint, either revolute, okay, or prismatic, either or. Okay, now if you have a system with a more complicated joint, like a bow joint, so what you will do is imagine like you have some links between the, like links with zero volume and zero mass, okay, and in between them you have just revolute joints. So that will in total make a bow joint. Okay, you will imagine still something like that. Okay. All right. Now it's mentioned here that you can extend this analysis to a branched mechanism easily. Okay, but not to parallel mechanisms. If you have parallel mechanisms, it's already something for advanced dynamics because you will need to work together with some constraint equations. Okay. If after this set of lectures you are not sure how to apply the method or apply the equations with some changes to a branched mechanism, ask me, okay? Because the logic is still the same. We analyze link after link, we analyze the forces and moments acting on each link, okay? So what happens in a branching point is not something too difficult, okay? Yeah, and the final thing I want to say here, we imagine like a fixed ground and point. So if I name the joints O1, O2, O3, and so on, O1, this first joint, could be either revolute or prismatic. Point O1 itself, the point O1, is fixed on the ground. Okay, so if this joint is prismatic, then this point would kind of split, yeah, and link 1 will go somewhere, okay, will distance itself from point 1, okay, and that distance would be the variable of that prismatic joint. So point O1 remains on the ground, okay? So this is our serial mechanism, link 1, link 2, link 3, and so on. Yeah, and you remember we will first do the kinematics forward and then the dynamics analysis backward. Okay, so before we start this kind of forward and backward, I wanted to specify all the parameters and the values we are defining. Okay, and maybe I'll state again, the overall idea is writing the Newton-Euler equations for each of these links in a manner that will allow us to easily extract the equations of motion. Okay, in a manner that will allow us to easily extract the equations of motion. So if there are n links here and n joints, oh, thank you. Thank you. If there are n links, n joints, and the assumption is each joint has a single degree of freedom, yeah. How many equations of motion will we need? Just n. Okay? And how many scalar Newton-Euler equations will we write? 6n. Good. Okay. So the first definition is this qk, which is called generalized coordinate, which is essentially the parameter that is used to describe the motion of joint k. So if if joint K is revolute, QK would be like one of the alpha, beta, theta parameters. Okay? And if joint K is prismatic, then it measures this distance along the axis of traveling. Okay, so maybe some kind of D or something like that. But to generalize, both revolute and prismatic cases, QK is the parameter used. Okay, so and it's called generalized coordinate. Okay, the second variable that is defined is here, generalized torque, tau k. So if you forget what is something, go back to this kind of glossary. So tau k, if it's a revolute joint, it's the torque, the torque that is acting between these links. Okay, now this is not an appropriate free body diagram, but it just to label the torque supplied by some motor, which is located here at OK, between the two links K-1 and K. Okay, so it's a torque, and here it is a linear force. It's a force if it's a prismatic joint. Okay, so tau k could be either force or moment, depending on the context, depending on the specific joint OK. And that's why it's called generalized torque. Okay, not just torque. Generalized torque could be also generalized force. Generalized force. All right, so it is either or. Now, if there is no motor in the joint OK, if there is no motor, then this tau k is 0. All right? Okay. Now the next thing is Fk and Mk. These are here, the force and moment exerted on link K by link K-1. So if this is link K, Fk is the force that the previous link, K-1, applies on this link. And Mk is the moment or torque that the previous link applies on this link. Okay? Remember, Fk, Mk are applied on link K by link K-1. Okay? This is not the sum of forces or sum of moments on this link. Okay? And obviously, if you look at link K-1, then minus Fk and minus Mk should be applied on it, right? On link K-1 as the reactions of these force and moment, right? Okay, now frame K, system of coordinates, we will attach a frame to each link, okay? So it is rigidly attached to link K, frame K. And if joint OK is prismatic, then you will normally have or normally assign frame K in the same way as frame K-1, because it will just move in a parallel manner. Okay. If not, it will normally rotate. You will normally assign frame K. If OK is a revolute joint, you will try to have the joint axis aligned with one of the axes of frame K. okay? Just so that it will be easy for you to define tau k and qk around one of these axes. And this is the rotation matrix from k to k minus 1. If you want to have one of the common rotation matrices, just assign your frames in such a way that you have this alignment with the axis of the joints. Okay, now look at the remarks here. If joint K is revolute, then QK, this angle, will appear somewhere in this rotation matrix. Okay, let's say QK could be some kind of alpha. So this will be depending on cosines and sines of alpha. Okay, whereas if joint K is prismatic, if frame K and frame K minus 1 are parallel, then the rotation matrix from K to K minus 1 will not depend on any QK. Okay, and in the simplest case, it will just be the identity matrix. Okay, just I. Okay, now next we have MK, the mass of link K, the non-bold GK, which is the point of the center of mass of link K, and the bold GK, which is a force, the effective gravity force acting on link K. So this one is mk times the gravity constant g, okay, in the as a vector, so in the right direction. Okay, I drew it downwards here arbitrarily, okay, but just to remind you that this is the bold one is the gravity force, okay. Okay, so next we have the inertia tensor of link K. Okay, this is here, and it is about GK in frame K. Okay, so I need to use that in this approach. Okay, and because just because frame K is attached to link K, yeah, it rotates with it. Just notice that all the components inside it are constants. Okay. And then I start defining some vectors that I will be using in this approach. So ROKGK, this vector from here to here. So this is OK, where we have connection to link K minus 1, and this is OK plus 1, where we have the connection between link K and link K plus 1. Okay, so we need all these vectors essentially, from OK to GK, from OK to OK plus 1, and from GK to OK plus 1. Okay. So this, and this. And I just wanted you to notice that this vector from here to here is a constant, always a constant, because point OK plus 1 is fixed relative to link K, okay, whereas point OK could be not fixed if it's a prismatic joint. So if it's a prismatic joint, link K will start distancing from OK. Okay, so if that is the case, say ROKGK, if it's a prismatic joint, will depend on QK. the parameter or the generalized coordinate for that joint. Okay, any questions so far? So far we defined the system. So what you need to do so far is kind of pre-code everything in terms of the geometry of the system. Just geometry, right? You can, if you are given a system, you can find all of these things. The masses of the links, you can assign coordinates, or parameters for the degrees of freedom that you have. You can assign frames, you can define all the rotation matrices. All of these vectors are just the geometry, right? No problem. Okay. And now this value here is the angular velocity of link K relative to K minus 1. It's the relative one. Okay, in frame K, we have two options. If OK is a revolute joint, we will have QK dot normally, if you assign one of the axes of frame K to pass through the joint axis. So we'll have QK dot as one of the components of this vector. Okay, one of the components, if you chose ZK to be parallel to the joint axis, it will be the last component. Okay, not necessarily you need to choose ZK to be parallel to the joint axis. Whatever you choose, the component here. And if it's a prismatic joint, then you don't have rotation of link K relative to K minus 1, so this will only be zeros. Okay? Clear? Lost? So this is this one. Angular velocity of link K relative to link K minus 1. Okay. So now what we can start doing is this. What we will do in this, we need to find this now, this and this, right? Right? We need to find these values. So what is, say for some link K, what is P? It is the mass mk times the acceleration of the center of mass of that link, right? So we will find that acceleration of the center of mass of link K, sorry, P dot, not P. We will find it gradually. Okay, link after link. We don't need to calculate from scratch every time. We can utilize what we just calculated for link, say, K minus 1, to extend a bit to link K, just for efficiency of calculation, okay, so that you don't start over every time. Okay, so we are doing it step by step. Okay, and similarly for H. Okay, so we will be utilizing the values in this manner that I will show you. It's written here. So in this page 2, what you have here is this forward kinematics. Now this thing here is yours, like the starting point. This is for link 1. Okay, this is done for link number 1. And this is done for link K, assuming link K minus 1 is already computed. Okay, so we'll follow this one. And this one is as long as, so not for link N. So everything except for the end. And this is a kind of preparation for next step, Okay. And specifically, you will need to construct the equations. Have a look here. So you have this value here, R01GK. Remember, O1 is a fixed point on the ground, and GK is the center of mass of link K, and this is double dot. So this is the absolute linear acceleration of link K. Okay, we will directly use this one times mk to construct the linear Newton-Euler equation for link K. And these ones we will use for the angular part. Okay, so we are going to prepare the absolute. Here we have absolute angular velocity and absolute angular acceleration of link K. Okay, so we are going to define it like that. All right. So let's start with the initial definitions. This is for link 1. I have it yellow here. I think it's the same, yeah. So what I have here is the same as here, yeah. So I prepare the absolute. Now I will just go through kind of nitty-gritty stuff here. I'm preparing everything for me to be able to use when I go to link number 2. Okay, so for link number 2, I will already look at these equations, knowing that, and I will substitute K equals 2, and then everything here with K minus 1, I already know. All right, because this is for link 1 that I prepared here. Okay, so this is the absolute angular velocity of link number 1. Okay, so 1 relative to 0, and I know this one. Why? Because at the beginning, remember at the beginning, we've defined K relative to K minus 1 for all of the links. Okay, this is one of the values we kind of predefined. Okay, so if link 1 is revolute, you will have something like 0, 0, Q1 dot for this one. Okay, something like. And if it is prismatic, it will all be zeros. Okay, now the dot here, the absolute angular acceleration, because I'm working in frame 1, according to the golden formula, this is the omega 1 prime plus omega 1 cross omega 1, which cancels out. Okay, so I just have the prime here. Is it clear? Okay, and now what I'm working on here is this vector, R01G1 dot. So just according to the golden formula, R01G1 double dot, okay, again, golden formula applied on the R dot. And R0102 dot and double dot, again, just golden formula for each, okay? Remember, R0102 double dot is something I have already. So I will use it later when I need, say, when I need RO102 double dot, here, when k equals 2, RO102 double dot will be here, already calculated. All right? Okay, next is these two equations. So the first one, absolute angular velocity of link K. What I'm doing, I'm adding the relative to the previous link with the absolute of the previous link. Okay, so omega k minus 1, this bit here is the absolute angular velocity of link k minus 1 expressed in frame k minus 1. When k equals 2, yeah, so this is omega 1 in frame 1, which we found, right? We found this one. So we can work with it. We first rotate it to the current frame, yeah, so using this rotation matrix, and add to it the angular velocity of link k relative to k minus 1. Okay? So that everything is now in frame k. So this should be clear. And now this second one is a similar idea. I'm using the absolute angular acceleration of the previous link. I'm rotating it to the current frame and adding. So So this is the relative part. This is also the relative part. I will show you why. So here is the kind of the y. Okay, this bit is the absolute angular acceleration of the previous link. Okay, plus everything you see here. Yeah, you see, it's like this value with the golden formula applied on it. Yeah, so this bit is the omega k relative to k minus 1 dot. Yeah, these two terms. Can you see that? Okay. So absolute of the previous link plus relative to previous link. So this link plus, relative to previous link. And now what I'm doing, this cross product, this omega k, I can substitute this one that I already calculated. So this is the substitution. And what you see here is this component omega k relative to k minus 1, part of it. So I will get it cancelled when I cross them. Okay, so I can already make it a bit more compact and only leave this bit. Okay, this is the only thing that survives. And this is the one that I copied here. Okay? Can you nod if yes? Yes? Okay. So remember, this is how I get the absolute angular velocity and acceleration for every link, and it depends on the absolute velocity and acceleration of the previous link. Okay, and we already have the values for link number 1. Any questions so far? Okay, so you see we are dealing with kinematics, going kind of forward with the links. Okay, now finished with the angular bits, and we need to obtain these values here. So ROKGK is simple golden formula. ROKGK dot and double dot. Again, simple golden formula. And then you can have a look here. O1 OK double dot. Maybe I'll specify here. So ROKGK so we have O1 somewhere here, GK, this is RO1 GK. This is what we are after. Yeah, so what I'm doing, I'm adding from O1 to OK, and then OK to GK, the accelerations. Okay, and how do I obtain each of them? So O1 OK double dot, I use, so this is it, and I use it from the previous calculation, yeah, O1 OK in K minus 1, and this is what you will have here from O1 to OK plus 1, kind of preparation for the next iteration. Yeah. So let's say if K equals 3, I will be able to find RO104 double dot in frame 3. And then when K equals 4, when I arrive to this place, I calculate, I already have 0104 in frame 3. Okay, so I can bring it to frame 4, like that. Okay? Okay, just, I guess, have a look how you are able to find all of these kinematic values without getting stuck. Yeah, how you will be able to find everything from one iteration to the next. Okay, have a look at home, I guess, but everything will be resolved well, okay? Any questions? Okay. So hopefully it will get clear, and these final ones are, again, preparing for the next iteration. Okay, so why are we doing it in this manner? We want to utilize previous computation to avoid doing redundant computations, essentially. We are trying to be efficient with our coding. Okay, so if you have a system with plenty degrees of freedom, I really suggest you follow this algorithm. All right? You don't need to remember these formulas or this algorithm by heart. You don't need to. As long as you understand the logic behind, you'll be fine. Okay? So, so far the logic is go from the beginning till the most external links, go like that, okay, outwards, let's say, to calculate your kinematic values. And avoid maybe repeating calculations. Now we are going to the backward stuff, and this is in this page and the next page. Yeah, so page 3 is backward dynamics, and this is for k equals n, like the starting point, and this is the backward dynamics for general k, link k, assuming link k plus 1 is already computed. Okay? So this we start doing this after we finished everything here. So we finished arriving till link n, and for all the links we know O1 gk double dot. We know omega k dot. We know for all the links already. Okay, this was done first. And now how to go back. Okay, so for this one, so yeah, maybe this is the split between k equals n and k equals, well, just k, general k. Okay, so for link, the last link, link n, yeah, you can look at the free body diagram for this link. And what do we have here? We have Mn and Fn, the moment and the force applied on this link by the previous link, link n minus 1. Okay, these are going through this joint. Yeah. By the way, one of the components here is either tau k or 0. Yeah, one of the three or one of these three. All right, and then there is the gravity force here. Now this is just general modeling, but if, say, if there is some external force applied on this link in addition to any of these drawn forces, you would add it. Okay, so you need to essentially adapt this algorithm to your specific system. Okay, but given no external forces on this mechanism, this is a correct free body diagram for the last link in the chain. Okay, now what is this equation? This is the linear Newton-Euler equation for this link. All right. On the left is the sum of forces in frame n, and on the right is p dot in frame n. Yeah. So this is the acceleration, the absolute linear acceleration of point Gn, the center of mass of this link, multiplied by the mass of the link. Okay, so kind of Ma equals sum of forces. What is this sum of forces? This Fn, taken all of this equation is written in frame n that is attached to this link, okay, plus the gravity force. Now the gravity force is normally easy to represent in frame 0, yeah, and just calculate the rotation matrix from 0 to n to adjust this vector of gravity, and you have the linear Newton-Euler equation for this link. Okay. Now, what do you do with it? What you can do is isolate this Fn. Isolate and find it like that. So I just moved this bit to the other side. Okay. Now remember, this is what? What is Fn? Fn here is, sorry, I have it here. Fn is the force applied by link n-1 on link n. All right. So let's take a break. Again, I'll be back again.
The acceleration is about the gn
Of g.
of g and
Yeah, this
yeah,
O1 gn.
yeah, but the force is of
The force acts on this point. Yeah.
so I mean the force
We are doing this equation. What happened?
Turn up it now.
Turn it off.
No.
Sorry.
Can I check it?
Yeah. You can't hear me. So this equation,
yeah.
the linear one, sum of forces overall, all the forces at all the points, all the external forces acting.
But it has to through the center of mass.
No, no. Thank you. Okay. Let's continue. So this this equation, sum of forces equals P dot, is this one. Sum of forces equals P dot. Any questions about this one? Okay, so remember this Fn is the force that link n minus 1 applies on link n. Okay? And what we can do is, just a second. Yeah, so what we can do is extract this Fn from this equation just by moving this to the other side. Okay, and then you can look at this thing here as already calculated. Yeah, in terms of Q1 until Qk and Qn and their derivatives. Because R double dot from O1 to Gn will depend on these parameters and their derivatives. Yeah, this R double dot. But we know how it depends. Yeah, because we calculated already the kinematics with all of this procedure. Okay, so once we get to k equals n, we would have found RO1 Gn double dot. That is this one, RO1 Gn double dot in frame n. Okay, so this is isolated. Now let's look at the angular equation, angular Newton-Euler equation. So on the left side is the sum of moments about point Gn, and on the right side is h dot about Gn. So now this equation. Okay, sorry, too messy. Sum of moments equals h dot, right? So sum of moments would be this pure moment, yeah, Mn. I'm writing this equation in frame n, all right? And then this force also does a moment about Gn. So this moment, in order to calculate it, I need the vector from Gn to point On. Yeah, so the vector from here to here cross with this force. So instead of going from here to here, I'm taking minus from here to here. Okay, so minus RON Gn, just because this is one of the values we prepared. OK, GK. Yeah, so ON, GN. So minus that vector would be the opposite direction from G to O. Okay, so the sum of moments, is it clear? Sum of moments about the center of mass of link N. All right, this is, maybe I'll put here, this is sum of forces of link N in frame N, and this is sum of moments about Gn of on link N in frame N. Okay, and this is Pn dot in frame N, and this is Hn dot about Gn in frame N. So what is H dot? It's the application of the golden formula on H itself. Okay, what is H? It's I omega Now, let me kind of do a side comment. So H about Gn, yeah, is I omega. So this is about Gn, n, like that, okay? Now H dot is, I would need to do H prime, yeah, this, plus omega n cross H. Yeah. Now this bit here is, or this bit, yeah, just fine, right? But this bit here, I just want to talk about. Yeah. So remember, I said I is constant in frame n. I of link n is constant in frame n. Yeah, so I need to do the prime, the kind of derivation. Let's do this. So h n gn prime equals the prime of this and because this is constant, I can kind of take it out, right? And be left with this prime, right? So this is just omega prime, omega n, yeah. And sorry, I'm a bit neglectful with the arrows. And if I want to get omega n dot, I would need to do omega n prime plus omega n cross omega n, which will get cancelled. So I'm left with this property, and then I'm replacing this one with the omega n dot. Why? Because I already kind of store it in the memory in that way as the angular acceleration. So what you can see here is the dot. So omega n dot in frame n is just like omega n prime in frame n. Okay, just because it is the absolute angular acceleration, let's say, of the frame in which you did the derivation, yeah, the same frame. Okay. So because you prepared this one, omega k dot in frame k, okay, in particular you have it for frame n, but for any other frame, this one you have it. Okay, for each of the links you have it with the dot. Okay. So any questions about this equation? No? So this is the angular Newton-Euler equation, the vector form of it. Sum of moments equals time derivative of angular momentum. Okay, for link n. And from this one, what I can do is isolate this mn, which is the moment acting on this link by the previous link. Okay, through the joint ON. And you can see that it depends here on this Fn. So this Fn appears here as I isolate my moment, but it was already isolated. So you can substitute it here. Okay, you should substitute it. And once you do, everything here on the right-hand side becomes some known expressions of your q1 till qn, your generalized coordinates, and their derivatives. Okay? So each of the things here, after the substitution, all here is already calculated or was calculated in terms of q1 until qn and their derivatives. Yes? No? It's important because when we are going to go to link n-1, we already know these values. Okay, so this is the free body diagram. So, okay, what we are doing now, we calculated for link n, we can move to link n-1. Okay, and similarly, we can kind of think, okay, let's say we evaluated everything for up to link k plus 1. How do we do the calculation for link k? Okay, so let's say this is the free body diagram of link k. Yeah. So when we did link k plus 1, we could calculate fk plus 1 and mk plus 1 in a similar way like here. Okay, so now we assume that we know that. Okay, maybe I'll just clarify. After we know Fn and Mn, if this is link n-1, we know that, so minus Fn and minus Mn act on it here, at joint O n, and at joint O n-1, we have still unknown f n-1 and m n-1. Okay, so these ones were already found. You just need to add the minus to them. Yeah, so you already found them. And there is the gravity force, g n-1 also. So you can do the free body diagram on this one. Write the Newton-Euler equations, sum of forces on link n-1 and sum of moments on link n-1 about point g n-1 and work in frame n-1. Yeah. You can write these equations and similarly isolate f n-1 and m n-1 from them. Okay, these are different. These are the sum of forces, sum of moments, whereas this is force and moment applied by the previous link on this link. Okay? So this is for a general link K, assuming that you found already these ones in the previous iteration. Okay? So sum of forces, you have, if I'm working in frame K, this is Fk. Yeah. Who applies Fk? sorry, link k minus 1. Okay, and fk plus 1 here with a minus. Fk plus 1, I just rotate it. If it was calculated in frame k plus 1, I rotate it to frame k by the appropriate rotation matrix. Who applies fk plus 1? Well, minus fk plus 1 is applied on link k by link k plus 1. Okay? And then the gravity force. So this is the sum of forces, and this is p dot, the derivative of the linear momentum. And from this one, I can isolate fk to serve me for the next iteration, okay? Going to link k minus 1. And so, okay, this is the linear Newton-Euler equation from which I can obtain fk. And now this is the angular Newton-Euler equation from which I will be able to obtain mk. Okay, so let's look at that. We are working in frame k about point gk. Okay, so what do we need to take into account? Not this gravity force, because it passes through it. So we need to take into account this moment and this moment. Okay, so this is mk, appears as is, and this is mk plus 1 with a minus, yeah, rotated from frame k plus 1 to frame k, right? Do you understand why I need the rotation? Because I calculated in the frame of the link. Yeah, so when I move to the previous link, I need to adjust the frame. So I will, when I write this in, say, when I move from link n to link n minus 1, here I was working in frame n, here I'm working in frame n minus 1. So whatever I calculated here in frame n, I will rotate to frame n minus 1 to substitute within these equations. Okay? So similarly here. And now I have this, this thing cross this thing, which is the contribution of this fk to the moment about gk. Yeah, so it is the vector from gk to ok cross with fk. Okay, so it is negative of the opposite direction here. And finally, the contribution of this force to the moment about gk, which is this one. Okay? And this is equal to h dot about gk, right? And I remind you, this is a general approach, so I'm using the general angular Newton-Euler equation, but if you have a specific system and for one link you can apply, if that link performs purely rotational motion, you want to apply sum of moments equals h dot about the center of rotation, you can. All right, so don't stick to this approach too blindly. You will need to make adaptations. Okay, now from here again I can isolate mk, and assuming that fk is substituted from here, from before, yeah, you will get everything here known in terms of the different qk or q1 until qn and their derivatives. Okay, so everything on the right hand side should be known in this stage already. Okay, so this is the example that I will use to demonstrate this this approach. So what you have here at the end is a reminder that for this Fk and Mk that you find in every for every link K, yeah, because you assume that well, every joint is 1 degree of freedom, either revolute or prismatic. So if it is revolute, you will have either 0 or the driving torque tau k in one of the moment components. And if it is prismatic, tau k will appear here, or 0 will appear here. Okay? So you have joints of 1 degree of freedom, yeah, 1 degree of freedom joint, and 5 constraint components or reaction components. So 1, 2, 3, 4, 5 of these equations will be, if you are only looking for equations of motion, you will not use them. Okay? If you want to find how these forces and moments behave over time, you will first solve the equations of motion and then go back to find how they behave. Okay, so what you have here is an example where you have your joint K, just an example as a revolute joint. Yeah, so this is, let's say, link K and link K minus 1. This is joint K, so this is point OK. And your assignment of frame has this as ZK. So ZK passes or parallel to the joint axis. That's why tau K, so you have this tau K actuation or driving torque about ZK. So this one is known and the rest are unknowns. Okay, so these will be the resulting 6 equations from the Newton-Euler equations on link number K. Okay, just rearranged so that these are the constraint forces and moments of joint K, and this one, the last one, has no unknown constraint component inside it, and this one will be the equation of motion. Equation of motion corresponding to this joint or to link K. So you will go collecting this special equation from each K. And this is how you will end with n equations of motion. All right? So this document here, I didn't print for each one of you, but this document is on LMS, okay? And you can have a look. It's for lecture 21 for equations of motion. So I will already finish this one. Yeah. So I'm skipping a little bit because I did go through it. Yeah, this is what I was explaining now. Yeah, just, I need to add the pointer. Yeah, so this is this example that I was going through now. Yeah, just to make sure you understand, if I have a prismatic joint here, instead of revolute joint, if it's a prismatic joint, and the axis is, say, axis of the prismatic joint, the distancing axis is, say, y, k, yeah, y of frame k, then what you will have here, you will have some kind of fkx, tau k, fkz, and mkx, mky, mkz. Okay? So tau k will be in one of these 6 components, depending on where the freedom is. Okay? And tau k will be as some kind of known torque or force applied by the actuator sitting in that joint. If there is no actuator, just replace that tau k with 0. Okay, but tau k is the known component. All right. So for every joint, through this approach, for every joint, we will be able to extract one equation of motion. Okay? This is if you are working in the frame that is attached to each link and you go in this order. Okay? Otherwise you will have a mess. You won't be able to extract these equations so easily. Okay? Now you are, because for every link you were able to find fk and mk in frame k, like that. And you can write this fk and mk like this, where one of their components is this known tau k. Okay, and the right-hand sides are all known expressions of your q1 until qn and their first and second time derivatives. All right. So you go collecting this kind of special equation, the equation of motion, for every joint, and you get n such equations. Okay, so tau 1 until tau n equals some expressions of your q1 until qn and their time derivatives. Okay. So this is what's written here, essentially. So I kept this equation, these equations, as star, equation star. I'll refer back to it. So this is the, let's say, raw set of equations of motion that you get in this approach. Okay, so set of n equations of motion that you get, okay, after applying this backward dynamics to all of the n links, okay, and every time putting aside the relevant equation of motion. Again, equation of motion does not have inside it any unknown components of reaction, force or reaction moment. Does not have inside it anything other than your q's and q dots and q double dots, okay, and the driving torques. Okay, it has to be clean of those unknown parameters. Okay, now here there is some kind of comments on how you can isolate the Q double dots. So I'll go through it quickly. We will not need it very soon. So what you can do, you will see that next to the Q double dots, essentially you can arrange these equations in this matrix form. You can just collect terms so that it is some matrix times all the Q double dots plus some matrix times Q dots and plus some matrix that doesn't contain any Q dots or Q double dots, and the vector of your generalized torques, tau 1 until tau n. So this matrix next to the Q double dots is called the mass matrix, and this representation is quite common in robotics. And what it is useful here to understand is just that we can isolate the vector of Q double dots. We can isolate it and it will be useful in order to numerically solve the equations of motion. Okay, I will show you why and how. So if you present your equations of motion in this form, yeah, you can just move this to the right-hand side and multiply by the inverse of this mass matrix and get your Q double dots. So essentially you want to isolate the Q double dots so that you can solve the system as a set of first-order differential equations. Because in this form, you have a set of, this is a set of n second-order ODE, ordinary differential equations. Okay, here you have n second-order differential equations, but your numerical solvers in MATLAB, let's say, or many others, are written to solve only first-order differential equations. So you will need to shift this problem of n second-order differential equations to 2n first-order differential equations. Okay, and in order to do that, a part of the process is to do it like a change of parameters. So you will define state parameters x, and x you will have as, let's say, all the q's and then all the q dots. Okay, so q1 until qn and then q1 dot until qn dot. These will be your 2n state parameters. Okay, and x is your state vector. And you will define x dot. X dot is q dot and then q double dot. So q dot, and the bottom line is the kind of isolated q double dot. Okay, so this is how you do it, or how you are always able to do it. Okay. Okay, so again, I will now need to demonstrate everything on this example. I will show you. So, by the way, here in this document, it explains this procedure of defining state vector. So, state vector, and bringing, so here, a kind of more simple way to explain, getting the q double dot vector decoupled q double dot vector, because you can get these equations with the the original equations, you get them with the q double dots all mixed. You will see that you will need to go through a stage of decoupling them to prepare for numerical integration of your equations of motion. Okay. I know you might be wondering why am I explaining that? I'll go back to the overall idea. You do your Newton-Euler analysis for each of the links. You grab the equations of motion, and those raw equations of motion, they are still not fully ready for numerical integration, to numerically solve these equations. So what you will need to do is to massage them a bit through this procedure. Okay, just algebraically manipulate the equations so that you can move from a problem of n second order ODE to 2n first order ODE that you can plug into a MATLAB solver. All right? Does it make sense? Okay, so here is the explanation of how to do that. And let's move to the specific example. If you want to follow me and you have a digital device, then just for lecture 21 on LMS, there is the accompanying document, so it appears on it. So this is the system. What I'm trying to show is how to apply this entire procedure on this system to end up with the equations of motion for this system. All right? So first, all of these definitions. Let's think about them. The QK, the generalized coordinates, are here theta. So theta is my Q1, and alpha is my Q2. These are the parameters I'm using. Okay? Is this a serial structure? Yes. Okay? It's pretty much just like the swinging wing here, this link that you had in the many examples I did before, just upside down. Same kind of system. Okay, frame K. So I need to attach frame 1 and frame 2. Frame 1 attached to link 1. Yeah, this is link 1 and link 2. So frame 2 is attached to link 2. Okay, I chose how to do that. Okay, now the rotation matrices from 1 to 0 and from 2 to 1, you can calculate, right? Tau 1 and tau 2, so tau 1 would be my actuation like that, and tau 2 would be about this axis, tau 2. Okay, some kind of actuation, or maybe in this direction. Better this direction, like alpha. Okay. Now for the masses, the center of masses, the inertia, it's all described in the text. Okay, so inertia about the center for each of these links. And all of the position vectors here, it's also defined. Now omega, we need omega 1 relative to 0 in frame 1, and omega 2 relative to 1 in frame 2. So what are these? What is omega 1 relative to 0? It's just theta dot about z1, right? And this one is alpha dot about y2. Okay? All right, so now you can start doing the forward kinematics. Okay, so you can go calculating each of these values for link 1 first and for link 2 second. All right, so this is done next. So this is like the beginning of all the pre-calculations needed, and then this is from here. This is the forward kinematics. So, sorry, starts here. This is for link 1. So this is for link 1, and this is for link 2. Okay. You can follow these calculations through the document. It will be too lengthy if I go one by one, but just look how it follows the same logic as this one. Okay, just have a look. And then from here, this is the dynamics part. So here I start from link 2. First, I start from link 2. This is the, so this equation here is like this one for finding F2 in 2. Okay, so this is the forces that link number 1 applies on link number 2. Okay, and because this joint is revolute, all of them are unknowns at this stage. Okay, and I can isolate them. Okay, so these equations, you can see how they, on the left hand side, I have all of these unknowns, and on the right hand side, everything is in terms of my, sorry, I think the microphone is gone. Yeah, just shut off. Sorry, too low battery, can't turn it on. So here everything is in terms of alpha, theta, and their derivatives. Okay, alpha dot, theta dot, and alpha double dot, theta double dot. And this equation is this one. Finding the moment that link number 1 applies on link number 2. Okay, so finding it. Now, this one has the tau 2 inside along the y direction. Why? Because this tau is along the y2 direction. Okay, y2 that goes into the page. Okay, this tau 2 is about the y2 direction. Can you see? This is the degree of freedom. Okay, it's a revolute joint. So one of the components of this will necessarily be your tau 2, and if there is no motor, it will be 0. Okay, so from this one, we are going to grab the equation of motion. Okay, the one that has no unknowns other than alpha and theta. Okay, so the middle equation here, this middle equation is what I just copied here. This is one equation of motion. Equation of motion, let's say number 1. Okay, done by first analyzing link number 2 in frame 2. Okay, and then we move with this approach to link number 1, now already knowing this F2 and M2. We already know them. Okay, so we need to find F1. Okay, so again, we are using now we are using this formula for Fk and Mk. Yeah, it's a bit long. Okay, but you can look at home and follow the logic. Okay, and here, so you find your F, yeah. Okay, so I just substitute all of these values, and then this F is substituted, say here you have this F substituted here into this equation. It's pretty long, as you can see, okay? But the important thing here, this is tau 1. This is the Z component. And remember, your link 1 is connected to the ground or to link 0. Let's say this is link 0 through a revolute joint that rotates about the Z1 direction. So this time, in the moment of the moment that link 0 applies on link 1, the Z component will be tau 1. Okay, so this is it. The Z component is tau 1. So from all of this monster, we need to only look at on the last component. The Z component will give us the equation of motion. Okay, so after you simplify it, this will be that second equation of motion. So equation of motion number 2. Okay, and now you have two equations of motion, and they are, well, not in this example, but generally they will have a mixture of theta double dots and alpha double dots. Okay, in this case, it's lucky you don't have it like that. But in order to proceed, you will need to isolate theta double dot and alpha double dot. So you will need that kind of algebraic logic to apply. And eventually, you can see what I did to isolate